there's no overhead whatsoever. All right, so what is machine learning? It's the textbook answer is the study and use of algorithmic or statistical models to perform tasks without explicit instructions. It's basically we're writing code that figures out the specifics of problems. So whenever we write code, we have to detail out, every exact thing that's going on, and we've all had this kind of example in our 140 classes, where you can sit there. If you ask someone, what are the steps to making a sandwich, and they say, okay, we'll get the ingredients. So how do you get all the ingredients? You got to open the fridge, do all of that. Essentially, what we're trying to do with machine learning is have the machine kind of detail out some of those specific steps. We give it a method or a way of tackling the problem, just like we would teach someone to solve like a mathematical problem, and then we let it go ahead and actually handle the solving of that problem on its own and figuring out the small details of it. By the way, if you guys have any questions at any point during the talk, feel free to just ask me. I want to make sure that everyone's online so that the demo makes sense. So why machine learning, and what's the power of it? Well, we can kind of frame this in the context of a really big and visual problem, which is self-driving cars, right? Self-driving cars is fundamentally a computer vision problem. And computer vision is one of the fields that machine learning applies a lot to. And the way we can kind of phrase how difficult this problem is that, well, for one thing, our brains are kind of like analog computers, right? And we've had, they've developed the capability to do what we would call feature extraction or semantic analysis, which is to extract meaning out of some arrangement of colors or position of pixels or whatever. But for a computer, especially if you're doing something as simple as pixel comparison, something like this sign right here would not be equivalent to this sign, even though we can both clearly see they're not left turn signs. Or this on a pixel value, or even if you use some kind of feature extractors, what we call them in computer vision, building is very different from this building, and how we would categorize them as building is not very clear. We can do it because our brains have developed the capability to, but we haven't articulated or otherwise defined how that process works. So we're essentially trying to find an algorithm so that our models can figure out what exactly distinguishes these as buildings. And we can even go something as simple as this. If we did a pixel comparison of these two things, this is a battery display of an iPhone 3G, whatever, without Retina display, and this is an iPhone 4 with Retina display. And you can see, even if the battery levels were the same, a pixel comparison would completely fail in this test. And these are very, very similar images, which is why we have to kind of develop these more complex algorithms and models. So that we can make something like this, where we can actually start accurately categorizing different things. So this is what we would call classification and segmentation, we'll call it. And it's finding different objects in different areas so that we can actually implement these things these things like self-driving cars. And the problems go far past this, like what if there's rain on the lens, right? It creates a whole different issue, or day and night look completely different from a pixel comparison standpoint and all that. And in the cutting edge, especially in deep learning, which I'm sure you guys have heard a little bit about, we've seen that we can kind of extract out all these different what we call features, or this is something that would represent semantic value. And these are things that look like kind of like nothing to us. They look like a bunch of different swirls, but these are the actual patterns that our models are recognizing that would ostensibly take us a really long time to figure out. And you can even kind of see the familiarity of some things. Like this right here is a layer in a neural network identifying flamingos. And you can kind of see the outline of them, and then the different colors represent different intensity or importance of certain pixels and arrangements and all. So some of the most, if you go and you look for the top 10 frameworks and libraries used by machine learning engineers, the top 8 you will see are these right here. And one thing that I want to point out about these is that half of them have nothing to do specifically with machine learning. Pandas and NumPy are specifically for data representation and manipulation, and Matplotlib and Seaborn are both for graphing and representing data. The point I kind of want to get across with this is that machine learning is kind of a subset also of data science along with AI. And working with data is a big part of working with machine learning. And Keras right here is actually a wrapper, or I'll call it a library for TensorFlow and Theano technically, but no one uses Theano. Scikit-learn is a nice place to start if you want to do some basic machine learning. They have a lot of statistical models, which means mostly like not deep learning kind of stuff, but linear regression like we're going to do today, polynomial regression, decision trees, all that kind of stuff. This is a good place to start. PyTorch is another popular library. So before we jump into this, and I'll reiterate it at the end of the talk, if you really want to get started in some kind of industrial level machine learning, I would start with scikit-learn a little bit, just to get used to manipulating data, reading in data, and using it, and then move on to something like Keras, or if you feel really ambitious, you can jump straight into TensorFlow. They are going to rework it soon to be a little more user friendly. So let's talk about what linear regression is. Linear regression is fitting an n-dimensional predicted line to a set of points, or to a set of data points. So a simpler point of this would be, or a simpler way of saying this would just be finding the best fit line on a bunch of data points, right? The line that is the best predictor of a bunch of nonlinear data points. And the reason we're going over this is because it entails an introduction to some of the core data science and machine learning concepts you're going to need throughout any career using machine learning or even data science in general. So the way that we would do that is, say we have this bunch of data points here. The best line that we would use to fit these data points are not exactly clear. And just to remind you guys, the formula for a line in algebra is just y is equal to mx plus b. In machine learning, we call these weights. So this m would be one weight. We call them weights because technically these lines can get n-dimensional or higher dimensional, right? So we go weight 1, weight 2, weight 3, weight 4. For now, we'll just call it weight 1. And this weight 0, which is a constant, we actually call a bias, because it's not multiplying by any of our factors or features, not features, but well, yeah, technical features or attributes of the data. But it just serves to shift the line by some constant amount to be more consistent. So I think we all could agree that this would not be an ideal line for the data set. And these are the values that we're using right now. So our bias, as you can see, is probably way too high. It starts nowhere near where the data starts, and the slope is actually about directly the inverse of what we want. So then if we change the bias to something better, but then change the slope to be a lot smaller, again, not entirely accurate, and it's not really something we would want to use. W1, which is our slope or our first weight, again, is wrong, too high, and then something that would actually look ideal is something like this. It might not be exactly perfect, but I think most of us could agree that this is just about what we want from an algorithm that gives us the best fit line. How do we do this? So the way that we change from this to this to this all the way back to something that looks reasonable, while there are a bunch of analytical methods of getting this right away, this process that we're going to use extends to the entirety of deep learning and a whole lot of machine learning. It's called gradient descent. So basically, what we're doing every time is we're checking how wrong our line is. And we can check how wrong our line is by the sum of the distances from each point. Right? So this line is actually pretty good because it seems to have a pretty small distance from all the points, everything considered. If this line was down here, the distance for these points would be very, very large, especially some points like this, and we would get a higher error, or what's we call error, but it would be more wrong, or it would be less correct. And the way that we kind of quantify this is by loss. And there are different types of loss, but the one that we're using specifically is called mean squared error. So what we do is we take the predicted value, and we subtract the actual value and square it, right? So let's go back to our example here. So let's say this is a actual value, or let's use one of them. This one is an actual value of, say, 80, and this is our predicted value of 60. So the error would be negative 20, right? 60 minus 80 squared, which would be 400. So we take the sum of all of those, so this would be 400, this might be, 160, and we square it so we don't get any negatives, right? Negative error would mean that it's correct, and just because it's above or below doesn't mean it's not, it's right or wrong. It's how far it is. So it's a matter of measuring distance. So we would solve all the distances or the errors from all of these and then get the average, and that tells us how wrong or how bad our line is, and we can optimize it based on that. So the way that we optimize it, and we can kind of look at this error as how bad it is, right? So we would want to make this as small as possible. And we can model this function in a 3D plane. So one axis here would be how our bias changes. Our b in y is equal to mx plus b, sorry. And then this other axis going into the screen there would be how our w1 or m or slope varies. And as you can see, it creates a nice 3D plane. So if we want to get to the lowest point, and we start, say, from the top here, it would make sense that at any point on our graph, we want to go where it is going down most rapidly, right? So we want to make it to the bottom, so wherever we are, we choose the path that is going down the fastest. Ideally, that'll lead us to the lowest point, but there are edge cases like, let's say there's this little divot right here that's not actually lower than this one, but because it's all the points from there are going upwards, we would just stick where we are. That's another issue that's addressed in more complex models, but for now we're not going to really consider that. We're going to consider our function to be what we call convex, like this, so that if we go wherever the loss function is decreasing the most, we'll eventually hit the minimum, which is what we call convergence, or our ideal value. So are there any questions on these concepts so far? Great, awesome. And what it'll look like is something like this. So as you can see, it'll keep changing and adjusting its values until eventually, after a whole bunch of iterations, it comes to something that's pretty reasonable for the line that we're going to use. Okay, so now's the time where we're actually going to start the demo. That's close. Well, whatever. You guys do need to download this right here, bless you. It's just going to be a CSV file that we are going to use for our workshop. And then I have all the code for it here. And we're only going to be using one weight this time. There is here, at this link, some code for doing it generally with any number of weights. And I'll tackle that a little bit more at the end of our talk. But if you go to this one and download that, so we can actually get started with our workshop. And I'll put the link to the GitHub back up at the end of the talk too, so you guys don't have to worry about that one too much. Does everyone have the data? Good over there? Awesome. Okay. So you'll just download this CSV. Let me grab this real quick. A CSV, for those of you who don't know, stands for comma separated value. It's pretty much the simplest way of showing a spreadsheet. And one thing that I do want to comment on, whenever we're indexing items in this, we always index row and then column. So if I wanted entry 5.2 or 5.1, I would go to the fifth, or technically it would be, so whatever. I'll go to the fifth row, first column, or 5.2 would be fifth row, second column. Of course, we do 0 and indexing, so it's not exactly accurate in this example, but we go row first, then column. So I'm going to download that, and then I'm going to have you guys go to a site called Replit. So I will actually sign out of this, just to show you how easy it is to sign up. You just type in repl.it, and then you can hit sign up, and you can literally just sign up with your Google account, which I'm sure you guys are all signed into. So you just hit that. It'll tell you that, throw your name in there or whatever. Hit save, and then you'll be able to make a new repl. A REPL is just a way of doing some cloud computing, I guess. It's just an easy way to write up some code and import libraries without having to do anything. Because we are going to actually be working with NumPy today. So you'll just click new REPL, type Python, and then create REPL. And it'll make that nice little thing for you here. And you should see a screen like this. So when you guys have done all that, let me know, and we'll get started with the actual coding part. Question? Let me make it bigger. So while you guys are getting that ready, let me talk a little bit about what NumPy does. So in Python, as most of you probably know, Python only uses lists and does not have arrays natively in it. Lists are fun and great, and they allow a lot of flexibility, but the problem with lists is that they're not as efficient as arrays. So what NumPy does is it allows us to actually have, essentially just have arrays in Python, which is nice because Python is easy to use and it allows for easy implementation of machine learning algorithms. So has everyone been able to get in to a Replit? Have any issues out there? I'm going to take that as a no. All right, so our first line that we're going to do, since we were mentioning Python, is we're going to say from NumPy, NumPy import, and we're just going to throw a star right there. This is kind of lazy, but I will tell you guys what that.
So after signing up, start coding now.
Yeah, it should be just.
Promise me to choose.
Yeah, just say Python. There you go.
What was the link for the data again?
It's, wait, pull it back up. It was this right here. So it's just tinyurl.com, CSS 2019, ML and data. Okay, so the first thing that we're going to do is actually create our function that we're going to use for gradient descent. Well, actually, let's do our main function first because it'll make a little more sense. So what we'll say here is we'll say if main or name is what main, yeah. Name equals main, and we'll define a function up here called run. Oops.
You have to
Yeah. There we go. Awesome. So for those of you who don't know, this basically just says that if you're running this one, then call this function, and it allows you to later use us as use the functions that actually run the file. So you can just throw this in a project somewhere and then actually use the linear regression function. So what we're going to do in here is the first thing that we're going to, well, before we do that actually, let's go ahead and upload the file that we just downloaded. So you're just going to click on the three dots here. You want you to scroll, move this open to see it. Click on that and you're going to click upload file. And then you're going to go to downloads and then grab the data.csv that was there and then upload it there. It should be pretty quick. This data is just some artificial data that's supposed to represent hours studied, I assume per month, because it's a lot of hours, and then graded in the exam, which this is some pretty tragic scores if that's the case. Can you imagine studying for 53 hours and getting a D? Jeez. Anyway. Once you've got that in, then we can actually start writing our code. So the first thing we're gonna do is we're gonna write gen from text. And then we're just going to pass in the name of our data, which is data.csv. And we're gonna specify the delimiter. The delimiter is what separates things in our file format, and as you might imagine, it's commas in a comma-separated format. Delimiter. So we'll just throw a comma here. Gen from text is a NumPy function. So if you didn't import everything from NumPy, it would be NumPy.gen from text. And it basically reads in the text from a CSV, from an Excel file, whatever you have, and then stores it in a NumPy array. The next thing we're going to initialize is our learning rate. So we have to kind of specify how much we're going to change online each iteration. If we end up changing it too much, it'll move around everywhere and it'll be really, really difficult to actually find the conversions or find the optimal point. If we move too slowly, we'll have to train it way too much to actually get there. So the learning rate that we're going to use for this one, and then you might also see it if you look at papers or stuff like that, represented by the Greek letter epsilon, is 0.0001. So 1/10,000 is what that is. And then we're going to initialize our weights. So our weights, as we described before, are the bias, which is the b or the y-intercept, and then the slope, which is m or w0. So we're going to say weights is equal to zeros. So what this is another NumPy function that creates a NumPy array of just zeros. And then we're going to call length points, which is, this right here should be points equal to gen from text. We actually have that in here. And we're going to create a new array that's a length of points, 0. So what we're saying by this is we're actually getting the width or the number of columns. So if I get points, that should be an S. If I get points 0, that is the first row in points. So if I go back here, point 0 is this first row. Points 1 would be this second row. Points 2 would be this one as well. So the length of this is 2. And as you can see, we're only going to have 2 weights. We're going to have our bias, and then we're going to have whatever is multiplied by this thing here. Okay, and then we're going to initialize. Right, we're going to grab our initial, just for comparison's sake, we're going to grab our initial W0, which is our bias, and we can say it's equal to weights 0, and then our initial W1, which is equal to weights 1. And you can just set it equal to 0, this is just for comparison. It's always going to be 0 in the beginning, but if you want to initialize it randomly or something like that, this is just to make sure that everything is general. Same thing here, I could just hard code a 2 if I wanted to do that, but we want to make this, easily extensible, so you can kind of just change this code a little bit, and then it'll be applicable to a situation with more weights than just 2. Okay, and then we're going to specify the number of iterations that we're actually going to do. And for this one, we'll do 10,000, which will actually go very quickly. And now that we've got our data kind of running, we'll come back to this after we actually define our gradient descent function. So once we've done that, we'll go above, and then we'll define our gradient descent function. And this is going to take in the points that we're using, our initial weights, so initial W0 and initial W1. Remember, W0 is the bias, so the constant, and W1 is what we multiply our X by. We're going to take in our learning rates, so that way we can, we're doing this so we can change our learning rate, so we can experiment with different things. And finally, our iteration count, or iterations. And then just a short, well, let's get another drawing, but we're just gonna do this real quick. 1 is equal to initial 1, that. And then we're going to create a for loop that actually goes and trains those weights over and over and over again until we get to a value that should be much closer to what is accurate. Find range. Oops, one more. Minus iteration. And what we're going to do is we're going to set our W0 and our W1 equal to the result of another function we'll call step gradient, which actually changes the grade or changes the weights by performing the gradient descent. Called step gradient, and we'll define this in a second. And we're going to pass it in W0, W1. There's a function in Python or in NumPy called array. And what we can do, well, I don't know if this is necessary, but I'm gonna do it anyway because I have the code. What this does is it takes anything that's list-like in Python and turns it into an array. So dictionary, oh, I don't know if it does dictionaries, but lists and some other structures in Python, it'll just turn into an array for you, which is a nice, convenient function. And then the last thing is we pass in the learning rate. Right, and then the next function we're going to define, which will be the last important one, will be our actual step, or our step gradients, which actually changes the weights, step, 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 gradients. And here we're going to write in our parameters, so W0, W1, points, so in here we need to find the gradient that we're going to use. The gradient is the direction that we're going to be changing. So we're going to initialize that to 0. We'll say grad W0 is equal to 0. And then we'll do the same thing with 1. 1 is equal to 0. And then we need to get the length of our training list, or the points that we're going to be using. And then we're going to call that n just to be mathematically consistent. So n is going to be equal to, and we're going to use it, we're going to turn it to a float because we're going to be doing some division later. Float, and then the length of, oops, that's length of points. Then we're going to go through all of the points, and we're going to be gathering the mean squared, or the mean squared, the gradients, or the error for each of our values. So for both our bias and for our slope, or or our W1, whatever you want to call it, M, all those things. So we're going to say for I in range, length, or actually, if we just put N, pretty sure we can. I'm gonna do length points anyway, because I don't know if it'll take a float or not. Let's just do that. But I'm pretty sure you can put N there. Then what you're going to do is we're going to grab the X and the Y. So the X is going to be the first entry. So when we go by row, it'll be the 0th column. So we'll say X is equal to points I0. And then Y is going to be equal to points I1, which is the volts. Something real good going on inside. So So, looking back at our data again, this is, column 0 and column 1. This is the hours studied, and this is the resultant, test score. So, our X and Y, respectively. Now what we're gonna do is calculate the gradient, and this is where the actual math comes in. So what we're gonna do is we're gonna say gradient W0 minus equals, because we wanna go in the negative direction of the gradient, right? The gradient shows us where it is increasing the most, so we want to go the opposite direction to get where it is decreasing the most. So we're going to subtract, and then what we're going to do is we're going to take y minus w1, which is our m, multiply it by x, plus w0. So as you guys can see, this is just y is equal to mx plus b, and we're subtracting it to get the difference. We're going to do the same thing with w1, the difference being that we're going to multiply it by x, because this feature or this element is actually being multiplied by x, like that. So it's going to go through and grab the gradient for all of the points that we're looking at. And then afterwards, what we're going to do is we're going to create the new W1 and W0. So what we'll do is we'll say new W0 is equal to, and we're going to take W0 and then subtract the average of the gradient over this over all these points. So what that'll look like is this: W0 minus 2 divided by n times the gradient of W0 times our learning rate that we specified earlier. So as you guys can see, this is going to directly affect how much the weights are changing by every time we go through and step the gradient. And then W1 will look pretty much exactly the same, but with W1 instead of W0. So let's grab that, write that there, W1, W1. And then lastly, we'll just return our new numbers. So return new W0, sorry. W0, new W1. So. Alright, technically we could stop here, and we have implemented our gradient descent, but we do want a way to check how effective it is, or how accurate it would become. So we are going to implement one more function, which is actually getting the mean squared error of our line at any given point in time. So I'll take it at the beginning when we haven't initialized it, it'll essentially look like a flat line, and at the end to see how much it's actually improved. So we're going to define a new function called compute loss. And this one is going to take our weights and our points, because that's all it needs to see what the line is and how far it is.
Also, in Python, function is the same as method, right?
Yeah.
Okay.
So the first thing that we're going to do is we're just going to initialize our loss variable, which will be 0 at the start, and then we'll start to accrue afterwards. And then we're just going to loop through all of our points, so we'll say for I. And this code is actually not the cleanest. There's a lot of ways you could clean it up, but that's the way I wrote it when I made this. So deal with it. For I in range points, so we're just gonna go through all of our points. And then in here, what we're gonna do is we're gonna grab our x and our y, much like we did in here. So I'm just going to copy this code and paste it right there. And then another point with just a little bit of math is you're just going to say loss plus equals, and then very similar to this thing here, except all we're gonna do at the end is square it. And that's how you raise things to an exponent in Python. So after this for loop, we'll just return the loss. Is everyone good with the code we have up here? Because I'm going to go back down to our run. Good, good. All right. So finally, we can actually run all of this. So what we're going to do after we specify our iterations, we're going to say W0, W1 is equal to radiant descent. And then we're going to pass in all of our arguments. So points. Initial W0, initial W1, learning rate, and iterations. So that'll actually do our training, and now what we're gonna do is we're just going to print out the results of it. So we will just hit print. And we'll say initial, it's your string. Error. And then we're going to do this thing here, which allows us to insert strings, or insert, to use format to insert values or other strings or whatever. 0. And then we'll have our initial W0. And our initial W1. And then out here, we'll put dot format. And we're going to call our compute loss function so that we can actually get the loss. Compute loss. And this W0, or initial W0, initial W1, and points, like so. The parentheses are getting a little intense here. And then just this last part will be initial W0, initial W1. I can actually, if most of you can see, I can zoom out a little bit so you guys can. Is everyone okay with that? Can everyone read that? Okay, good. And our second one will be pretty similar. We're going to grab all this.
Can you zoom in slightly to clear the?
Sure.
There you go.
Let me grab this real quick. Right in there. And we're just going to change this to final or after or whatever. Final. And then we'll change these to W0 or W1, sorry. W0. And then this one to W0. W1. And once we do that, we should be able to actually run it. Let's stop here. let me grab this real quick because I do have it. I know for a fact this works. I might have misspelled something. And the code that I have on here is actually going to create a. Yeah, okay, this one works. The code that I have on there is actually going to create. So this code should be the same except get rid of this, and then everything else should be pretty much the same. It just has some comments. So I'll have to look at what this is here, and I'll put the GitHub up there to show you guys. But the what you should get is it'll show the initial error. Our initial error is really high, over 5,000, and our initial W0 and W1 are both 0. And after 1,000 or 10,000 iterations, our error comes down to 112, which is actually pretty small considering that it's a squared error, not just a flat difference. Our W0 is 0.6, yada, 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 so we're something around 0.6, and our bias or y-intercept is about 1.467. And actually on the GitHub, I actually have code to use Matplotlib, which is another one of the libraries that was on there, to actually display the points and the prediction line. So if I can actually show this here, on the laptop. Okay, well, it's not wanting to cooperate.
Do you know?
Yeah, if you could check it out, just a second. I just need to show my laptop. Just one. I think so, yeah. My laptop's kind of freaking out. Should be the VPA one. I think it's probably also the laptop. It's just freaking out. Alright, well, I got it here. It's okay, so you can put it back to whatever it was before. Yeah, I just took the.
I think it's
Alright, it looks like our display actually just broke right now. But I can write I'll write the link. Oh.
Yeah, I don't know why it just did that, but okay.
So, what you should get is you should get a if you follow the code link, you should get a graph that looks like this. So all these black dots are going to be, I just literally screenshot from my laptop right now. All these black dots are the points at which the real data is at, and this blue line right here is our predicted line. So I'll throw the link to the GitHub up on the screen again, so you guys can, double check it there. I'm not sure exactly what happened there. It was having some issues, it didn't, look like it imported NumPy there, which I'm not sure why it didn't, but the code is mostly the same, it's probably just, some small issue there.
So does the computer just generate numbers and then just test it constantly?
So the way that it works is that it checks each point and sees, and takes the mean squared error, which is the square of the difference between the two, and then it adds it together into the total error. It uses that total error to, then adjust the weights based on how far they were before, to get to something like what we saw, in this slide here. So like I said, you guys can go to this link right there, and then there's both the code for this, and there's a code for the general case that you can use with any number of weights, as long as it's in a similar CSV format. So do you guys have any questions? Is anyone hitting bugs like I was? Okay, cool. Let me look at it real quick to see what's going on. I did? Okay, where is it?
What are the, yeah.
Right, okay, cool, thank you.
Hey, you're done?